Welcome back to the Generative AI Playground. Today, we are diving deep into complex reasoning structures, specifically focusing on how to break down problems using chain of thought prompting. Let us kick things off by exploring one of the most powerful prompt engineering techniques, chain of thought, or COT. As generative AI models grow in complexity, they can sometimes struggle with tasks requiring deep logic if asked for an immediate answer. COT solves this by encouraging the AI to think aloud or sequentially work through its reasoning process, much like a human would when tackling a multi-step problem. Why does this matter? It significantly enhances the transparency of the AI's decision-making process and improves the accuracy and reliability of its outputs. Instead of forcing the model to jump directly to a conclusion, a COT prompt lays out a reasoning chain or train of thought for the model to follow. A prompt may start with background context, state a hypothesis or problem, provide reasoning steps, and end with a conclusion to be expanded on. This technique is especially valuable in educational applications, complex problem solving, and scenarios where understanding the rationale behind an answer is just as crucial as the answer itself. It transforms the model from a simple text generator into a transparent reasoning engine. This flowchart illustrates the fundamental mechanics of chain of thought prompting. We begin with a complex problem, feed it into the chain of thought prompt structure, and force the model to sequentially navigate through background context, hypothesis formulation, and discrete reasoning steps before arriving at the final answer. This prevents the model from taking cognitive shortcuts that lead to hallucinations.
Let us break down the exact anatomy of a chain of thought prompt using a practical mathematical example. Imagine we need the model to calculate the total cost of painting a room that is 5 meters long and 4 meters wide, at a rate of $3 per square meter. If we simply ask for the total, the model might hallucinate the math. How do we apply COT here? We explicitly instruct the model, describe your process step by step. The model's response then follows a structured logic path. First, understanding the problem. The task is to calculate the total painting cost based on dimensions and rate. Second, breaking down the problem, finding the room's area, then calculating the cost. Third, calculating the area, multiplying 5 meters by 4 meters to get 20 square meters. Fourth, determining the total cost, multiplying 20 square meters by $3 to get $60. This intermediate step is crucial because it translates the room's dimensions into a single value representing the total surface to be painted before proceeding. It is literally forcing the multi-billion parameter neural network to show its scratch pad. Observe the execution path of our painting problem. The model identifies the goal, breaks down the problem, executes the area calculation, feeds that intermediate result into the cost calculation, and securely arrives at the final $60 output without any guesswork.
In prompt engineering, we can apply chain of thought in both zero-shot and few-shot scenarios. What is the difference? Zero-shot COT is when we append a magic phrase like, "let's think step by step," to our prompt, without providing any previous examples. The model relies entirely on its pre-trained knowledge and self-guidance to formulate the reasoning chain. While this is easy to implement, for highly complex enterprise tasks, it might not be enough. This is where few-shot COT becomes indispensable. Excitedly, in few-shot COT, we provide the model with a few concrete examples that establish a concept or scenario, specifically showcasing the exact reasoning steps we expect it to take. Pause. For instance, if we want the model to analyze pros and cons of renewable energy, we provide a mock interaction. We show a user asking a question and the assistant responding with a carefully structured chain of thought detailing environmental impacts, cost factors, and spatial requirements before concluding. Very fast. By analyzing these examples, LLMs learn the specific pattern of reasoning expected for that domain. It tightly constrains the generation process, making the final outputs incredibly precise and aligned with your business logic.
This diagram contrasts the two strategies. Zero-shot COT simply appends the think step-by-step directive, while few-shot COT injects meticulously labeled reasoning examples into the prompt payload. Both converge to produce vastly enhanced logical output.
Let us elevate our understanding to advanced code of thought variations, tree of thought and maieutic prompting. Tree of thought prompting is a specialized case of chain of thought. It leads the model to come up with one or more possible next actions. How is it different? It operates in a tree search manner, where the model runs through possible next steps across multiple branches. For instance, if asked about climate change effects, it might branch into environmental effects and social effects, developing each independently. Next, we have maieutic prompting. Here, the model is provided with a question and an initial explanation. It is then requested to elaborate on certain parts of that explanation. The fascinating part is the pruning. Trees that offer wrong explanations are removed, or if they are right, they are pruned to focus the logic. This significantly enhances the performance of the model in challenging common sense thinking tasks. For example, if asked, what are clouds made of? It answers water droplets or ice crystals, and then maieutic prompting forces it to independently verify and expand upon the definitions of droplets versus crystals, ensuring absolute factual rigidity. Behold the tree of thought architecture. The initial query splits into multiple logical branches. Each branch undergoes an elaborate and verify stage, characteristic of maieutic prompting, where invalid logic is ruthlessly pruned before reaching the final cognitive state. Two more sophisticated variations of COT exist: complexity-based prompting and generated knowledge prompting. Complexity-based prompting involves generating many chains of thought simultaneously, or rollouts. The system then selects the rollouts with the highest number of reasoning steps and chooses the most often repeated end conclusion. For a difficult math question, the model performs several rollouts. It considers the ones with the longest chain of calculations. The rollouts that converge to a similar answer are selected as the definitive solution, filtering out statistical anomalies. Then we have generated knowledge prompting. This method forces the model to generate the appropriate foundational facts before continuing with the actual request. For instance, if a user requests an essay on the impacts of releasing carbon dioxide, the model must first generate statements like, releasing carbon dioxide causes climate change, and it results in loss of biodiversity. Only after establishing these key facts does it proceed to compose the essay. Since the model is explicitly conditioned on these pre-generated facts, the completion quality is massively enhanced, and the risk of hallucination is minimized. This flowchart outlines generated knowledge prompting. The user prompt triggers an initial phase, where core facts are explicitly generated. These facts are then fed into the conditioned generation phase, anchoring the model to produce a high-quality, fact-based output. Theory is wonderful, but let us look at exactly how this code works in an AWS environment. To implement chain of thought programmatically, we use the Amazon Bedrock API via the Python Boto 3 SDK. We need to structure our JSON payload to explicitly demand a reasoning chain. We will use Anthropic's Claude 3 model, utilizing the Messages API format. We construct our prompt string to include the background context, the problem, and the critical instruction. Describe your process step by step. It is highly recommended to use XML tags within your prompt to separate the context from the instructions, as Claude is specifically trained to recognize these boundaries. Once the payload is constructed with our inference parameters, like setting a low temperature for analytical tasks, we invoke the Bedrock runtime client. The model will stream back or return a JSON object containing not just the answer, but the entire logical pathway it took to get there. Let's analyze this Python implementation. We initialize our Bedrock runtime client. We construct prompt data using XML context tags to provide background, followed by our specific question and the crucial COT instruction. Think step by step and lay out your reasoning chain. We package this into the messages array required by Claude 3. We set temperature to 0.1 because we want highly deterministic logical reasoning rather than creative fiction.
We invoke the model, parse the JSON response body, and print the generated text, which will elegantly display the model's step-by-step deduction process. The execution flow is direct and powerful. The Boto3 client packages the COT prompt payload, transmits it via the Invoke Model API to the Claude 3 model on Amazon Bedrock, which processes the logic and returns a comprehensive step-by-step JSON response.
While chain of thought is a formidable technique, we must address its enterprise trade-offs and best practices. By forcing the model to generate intermediate reasoning steps, you are inherently increasing the number of output tokens. This means the approach makes the output slower and costlier. You are paying for the model to think. Therefore, COT should be reserved for complex reasoning tasks, not simple factual retrieval, where a zero-shot prompt would suffice. How do we evaluate if our COT prompts are effective? We employ structured evaluation frameworks like RACA: relevance, accuracy, completeness, clarity, coherence, and appropriateness. You must meticulously evaluate the generated reasoning chain for logical coherence. Does the argument follow a logical sequence? Are there contradictions in the intermediate steps? If so, you must iteratively refine the prompt, perhaps by providing more precise few-shot examples or utilizing meta-prompting techniques to correct the behavior. Excitedly, mastering COT allows you to unlock the true cognitive potential of foundation models. We invite learners to like, subscribe, and visit quicktechie.com for premium and for recently updated material as per latest syllabus and certification prep, Q&A banks, ebooks, audiobooks, full training, interview guides. On YouTube, it may not be a latest contents. This represents the enterprise optimization cycle. We deploy the COT prompt, analyze the token cost versus value, and evaluate the output via RACA. If the logic is incoherent, we perform iterative refinement. If coherent, we scale confidently in production.